Hi and welcome to this section where we would like to look at numerical differentiation. So our aim is to find the value of the derivative of a function f at a given point. So now, remember in the study of our forward differences and the shift operator, we had this relationship here. I think we derived it somewhere. That the forward difference operator equals to the shift operator minus 1. And we also had this one here, that where we found out that d is the differential operator, and then we say it equals to the log of the shift operator here. So from this, okay, we can now have that hd equals to the log, where e, the shift operator, we make it the subject here. We know that now the shift operator can be given as the forward operator, forward difference operator plus 1. So which we get here, this is the shift operator here, okay, where shift operator is equals to the forward difference operator plus 1. And then next we make the differential operator here the subject, and now this here, I wrote down here something either from the Maclaurin's or the Taylor series expansion of log of 1 plus x. Okay, so we know that log of 1 plus x, the expansion using either Maclaurin's or Taylor series expansion, is given by this expression here, x minus x squared over 2 plus, the signs keep on alternating, and it is x to the power 4 over 4 plus x to the power 5 over 5, and so on. And so we use that same knowledge to come up with the expansion of log of this shift, forward difference operator plus 1. So we have 1 over h into this minus the forward difference squared, second forward difference over 2 plus the third forward difference over 3 minus, and so on and so on. Okay, so now that is the d, and then we can also get the d squared. The d squared is quite it's not involving, it's just a few minutes here. D squared, we know we have d, so d squared, you just get this expression for d, our expression for d here, and then you try to square it. So when you try to square it up to at least the term in power 6, yes, you can sit down on a nice cup of tea and make sure that you get there's something from similar to this expression which I got here. I try to color code it just so as to make it easy for us to follow. In other words, here the one in blue is the one in black. Of course, when you square it, d squared is equals to the expression for d we have here. Then you square it. Of course, the h is already squared here. So when we square this term here, okay, then you try to multiply this term into the whole expression again. So you end up with this expression here, okay, which I try to, it's just some bit of patience. You just sit down and try to expand the terms, okay, use the algebra now. And then in here I try to collect like terms, okay, again with the color coding, just to make sure that it is easy to follow. The cubic terms, the terms which are squared, the terms which are raised to the power 4, and so on. And then this is the expression which we come up with, okay, for the expression for d squared, 1 over h squared into that. So if you have the expression for d and 1 over h squared, then we can define, we know, we have already seen that f of x, the first derivative here, which can be written as derivative of f of x with respect to x, okay, and we say that it is the same as d f of x, where d is the differential operator. But we already have the expression for d, which we have here, this one here in red, so that this is d. So d of f of x, you know, is going to be this. Then you just replace here f of x throughout, okay, f of x and f of x. So what we have here, d of f of x, is just exactly what we have there, where we have 1 over h, the first forward difference, minus the second forward difference, plus the third forward difference, minus the fourth forward difference, and so on, in that particular pattern, okay. And then we already saw, or we know, that the second derivative, which is the derivative of our function f with respect to x, okay, the second derivative, which can be written as d2 f of x, now is going to be 1 out of h squared, then the expression we have just here, this one here, f of x. So what we have here is f of x, f of x, f of x, and this is f of x. So it is 1 out of h squared, second forward difference, minus the third forward difference, plus 11 over 12, the fourth forward difference, minus 5 out of 6, the fifth forward difference, plus, and so on, okay. Yeah, so that's all. One, what did we start with? We started with the expressions here, okay, these expressions which we saw last time. Then we made the differential operator here, the differential operator the subject. Then we used our knowledge of the expansion of log of 1 plus x from the Maclaurin's or the Taylor series. We expanded it, and then we got this expression which we can square, and then we get this expression for d. And then we use the fact that we know that the first derivative here is simply d f of x, and the second derivative here is simply d squared applied on f of x, and then we fill in appropriately. So similarly, if we use a backward difference operator, the same. We already have this expression derived in our notes, okay, for which we can now have the expansion here of what is it, you can either have this expansion here, log of 1 minus the backward difference operator to the power negative 1, which is the same as log of 1 over 1 minus that, okay. That should be familiar to the expansion of log of 1 over 1 plus x, okay, which should be able to give us this expression here. Then when we square this expression, this d, okay, d squared is equals to 1 over h squared, then we have what we have here, then we square. Again, if we use, you know, just to be patient, some little patience, and then we follow the procedure as above for the forward difference, we should be able to come up with this expression here. And then if we were to use a backward difference operator, we know that the derivative here, which is d f of x with respect to x, simply d f of x is now going to be equal to 1 out of h times the backward difference operator f of x plus the second backward difference operator divided by 2 plus the third backward difference operator plus the fourth backward difference operator, and so on. Okay, similarly, if you want to find the second derivative, okay, which is that, which is this, then it is just 1 out of h squared, then times, we are using this expression now, okay, then the second backward difference operator plus the third plus 11 out of 12 times the fourth plus this. Okay, yes, so we look at an example here where we would like to compute the derivative of f at the point 0.2 and the second derivative of f at the point x equals to 0 from the following tabular data. So just to save time, we have the tabular data given to us here for various values of x and their corresponding function values. Okay, we would like to put here in a table, we have our x values in the first column, and then in the next column our f values, and then the forward differences in the preceding columns, which by now we are familiar with. So we'd like to find the first derivative of f at the point x equals to 0.2, this one here. Okay, so like you see, okay, maybe at x equals to 0.2, maybe we can write it down here. So we are going to say, I will write it down just for us to remember. So we have said that this equals to that, and we have it as 1 out of h, okay, times the forward difference here, if we are to use the forward difference here, minus the second forward difference plus the third forward difference. How many differences do we have here? We have up to the fourth, the fifth is 0, so we shall write up to the fourth here. Okay, so the rest is just a matter of substitution because we have everything here. H is 0.2. Okay, this step length here, it is uniform 0.2, 0.2. So H is 0.2, and then the first forward difference here is 2.40. So in here we are simply going to look at here, we are going to look at the first forward difference, okay, evaluated that this is the point x0, and this is the point x1, this is x2, this is x3, and this is x4. So what would this value here be? This would be the first forward difference evaluated at the point x1, because this one here, the first forward difference here, remember this one here is given by it is given by f of 2 minus f of 1, okay, this value here minus this value. So anyway, this is the first forward difference we pick, and then we shall pick values along this diagonal here as the forward differences we are going to use. Okay, so in here we have the first forward difference evaluated at that point x1, and then the second forward difference, which is going to be 8.00 divided by 2, and then the next forward difference divided by 3, and then the next forward difference, okay, that is the fourth, divided by 4. So the answer you get here should be, you know, the derivative of f at this is the derivative of f at the point x equals to 0.2. X equals to 0.2, and then you get the answer. Now if you want to get the second derivative at the point x equals to 0, this is going to be d2f of x, which is 1 out of h squared, to the expression we had the second forward difference minus the third forward difference plus 11 over 12, the fourth forward difference, plus so on. Again, we simply substitute. This is 0.2 squared, then the second forward difference is now, you realize now the second forward difference, we simply start from where's the second forward difference? Just a minute. Yeah, we simply start from let me see. Oh yeah. So we are now at the different point. Sorry, I was still thinking about the point x equals to 0.2. We are now finding the second derivative at the point x equals to 0, 0. So this is the point x naught here, and then this is its function value, and then this is its fast forward difference, okay, and then this is the second forward difference. So for this one here, we are moving along this diagonal here, okay, this fast forward differences here. This one here in blue for the point x naught equals to 0.0, while this one here in red, remember that we are finding the first derivative for the point x equals to 0.2. So that means that we fill in the values in blue, and what do we have? The second forward difference here in blue, which is this is the second forward difference, 2.24. So we have 2.24 plus minus the third, which is 5.76. This one here, this is 5.76, then plus 11 over 12 times the fourth forward difference here, 3.84, and then for which we shall get the solution. Okay, so we have looked at an example here where we have used the forward differences to compute the derivative of the function, the first derivative of the function and the second derivative at various points. So you can go through, because these examples are also in the notes, so I've simply illustrated how it's done. You can go out and check out for any errors or anything you didn't understand and just put it in the comment section. Okay, thank you, and in the next video we shall look at further examples of solving, and here we shall be using the backward difference operator. Thank you, and see you in the next video.